Hi students, today we'll discuss one more topic, that is waves. In this we'll do some parts, part 1. Okay, so first of all, what is meant by a wave? See, we are talking, therefore a sound is traveling right from one point to another point and it is reaching to the ears, so therefore we are able to hear. Therefore this sound is nothing but like a wave. Even light is a wave. We are talking in a phone, no, that is electromagnetic waves, right? So what this wave it will do? What is a wave? What is a wave? Wave is nothing but a disturbance created in the medium, right? So you need to create one disturbance, no, in the medium. See, if there is no disturbance, no sound it will be created. Suppose if you are talking onto this one, no, therefore it will create some disturbance onto this. That disturbance, no, will be carried out throughout the medium onto this. Like a water is there, a flat, right? There is not disturbance, water is there. Suppose if you drop a stone in that, so definitely it will create a disturbance in that one, no? Therefore it will forms like a waves, so like a water waves, and it will travel in all the directions. So wave is what? Or you can wave is nothing but like a disturbance created in the medium. Like you can take one metal rod. Therefore, if you try to disturb at one end, no, definitely that vibrations, no, it will travel throughout that rod onto this. Is it? So this is nothing but a disturbance. We'll call it as like a wave, right? So what the wave will do? Wave will propagate. So and it will transfers. So energy and information now, right? So therefore here in this propagation now, right? So how many types of waves are there? Let us see. So there are classified these waves, no, based on the requirement of the medium. Therefore these waves are classified into, so let us take these three categories based on the medium requirement. Medium. So the waves are classified into, therefore, three categories. No, one is mechanical waves. Mechanical waves. Clear? So this mechanical waves requires a medium. Compulsory, it require medium for its propagation. Yes or no? Without the medium, these waves will not travel now, right? Next one is another one more, that is nothing but electromagnetic waves. These electromagnetic waves, electric field and magnetic field, so it will create like a, so one electromagnetic wave. We'll study these topics in second year concepts now. So where electric field and magnetic field, so will result and gives us like a electromagnetic wave. This does not require any medium, even it can travel in the vacuum, right? So our light, so is nothing but our electromagnetic wave. We are talking in the phones, that waves also nothing but a, so electromagnetic waves now. Clear? So therefore next one is what? Matter waves. What is this one now? Matter waves. What is this matter waves now? Therefore if a matter is moving, like if one particle is moving, it will move in the form of like a waves, like a de Broglie wavelength, no? So like we already studied, right? So we'll study this topic is also dual nature of the light, no? So in the second year concept. Therefore so de Broglie's wavelength. Therefore wavelength is equals to h by p. That means if a particle is moving, it will move in the form of like a wave. Suppose if we are moving, therefore we will be also moving in the form of like a wave, but we do not see any wave, right? Wave nature. Why? Because it is inversely proportional to the momentum. So for our body, therefore momentum is larger now because mass is very high and Planck's constant is very smaller now. Therefore, so we cannot able to visualize the wavelength if we are moving. If an aeroplane is moving, it will be also moves in the form of a wave, but we cannot visualize. If you want to visualize, no, so therefore it should be like a very smaller particles, no, we can able to visualize, right? These two topics, no, so we'll study in the class 12 topics, no. So in this part, therefore we'll study fully focused on mechanical waves, which requires the medium, right? So mechanical waves, therefore which requires the medium for its propagation. Without the medium, it does not move on to this. Like our sound waves, water waves, right? So this all comes under like a waves in a string. So this all comes under like a mechanical waves. Again, based on the propagation. So therefore, based on how they are going to travel, no, based on the way of traveling, no, again classified into two categories now. So what are they now? Mechanical waves. So therefore here one is progressive waves. Next one is stationary waves. So progressive waves and stationary waves. So what are progressive waves now? Therefore once it is disturbed, so it will travel and travel and it will never return back to us. Therefore it will goes on traveling until its energy is getting dissipated. That type of waves are said to be like a progressive waves. Suppose if we are talking, so therefore that wave what it will do now, it will travel in all the directions and it will never return back to us, right? These type of waves are said to be like a progressive waves. Once the disturbance is started, it will travel until energy is dissipated and it will never return back to us, right? Energy is propagated in all the directions now. But what about the stationary waves now? These stationary waves, in the name itself is there, stationary waves are standing waves, no? So therefore mostly these waves are takes place in the string, right? So if you create one disturbance, no? If you create one disturbance, so this wave, it will travel to here, it will travel to one end, and again after from here, no, this end, again it will be returned back to us. So therefore again it will come back to this one, no, again, so this wave, again it will travel. So therefore this wave, it will be get trapped between these 2 points only. The energy is trapped between these 2 points. So these type of waves are said to be stationary waves or standing waves. Now, so we'll discuss progressive waves. So what are progressive waves now? So once, right, it is created, no, therefore it will travel, so until its energy is got dissipated. Now this wave, right, it will goes like this only and it will never return back to us, right? We know starting point, but we don't know ending point onto this, or no, goes on until energy is getting dissipated. Now again these progressive waves again classified into again two categories now. So what are these two categories now? This one is longitudinal waves, next one is transverse waves. So longitudinal and transverse waves. So we'll see the basics related to this transverse wave and longitudinal waves, no? So these longitudinal waves and transverse waves. See, therefore this classification is based on the particle vibrations onto this. How these longitudinal vibrations or longitudinal waves it will travel, no? So the best example for longitudinal waves is our sound waves, no, right? So what we are doing now, we are talking onto this one, no? Therefore we are creating disturbance. What will happen now? These air molecules which are there, no, it will got disturbed. So when it is getting disturbed, therefore these particles, no, will be started moving toward this side. So once it is moving toward this side, so therefore it will go and it will collide to the other particles, like all the particles will come closer. So then afterwards it will exchange the energy, then afterwards it will go back onto this, right? Again it will come closer, no, it will go back onto this, like that. So all the particles will be coming closer and going far away, coming closer and going far away. Like this, the particles are going to vibrate now. So here, if suppose this is a wave, right? So this is a wave which is traveling, this is the direction of your wave, no? So therefore these particles, how the particles are there now? These particles are gain the energy, these particles will go closer onto this one, no? All the particles will come closer here, no? Closer, and then afterwards it will go far away, again it will comes closer here, no? So it will comes closer here, no? Therefore again it will go far away onto this. Therefore all the particles are very, very closer to here, no? This we can call it as like a compressions. And all the particles were going far away onto this one, no? This we can call it as like a rarefaction. Clear? So compressions and rarefactions now. So how the particles are moving now? This is your direction of your wave. All the particles are moving like this. That means this particle is going toward this side like this. Therefore, these particles, so how they are moving now? This all the particles are going parallel to the direction of your wave, right? So therefore here like this. This side is a wave is traveling, therefore these particles are coming closer, going far away, coming closer, going far away, right? So how the particles are vibrating? No, the particles are vibrating the parallel to the direction of your propagation. So therefore these type of waves are said to be like a longitudinal waves now. Longitudinal waves. So here, so when compressions takes place now, therefore the pressure will be high. So here when rarefaction is taken place now, so pressure will be low. Yes or no? So compressions, therefore here the compressions and rarefractions now. Clear? So therefore this longitudinal waves now. So in this way it will take place no. So therefore this is said to be like a example for sound waves. Clear? Here this longitudinal waves is we can call it as also pressure waves now. How the transverse waves will be there now? The transverse waves. So therefore you need to take one rope here no, like one rope, like a water waves also is there. Water waves what it will do? It crust and trough like this. So R one rope you take it no, therefore you try to give a jerk onto this. So therefore the wave it will be able to go in this way. So this type of waves are said to be like a transverse waves now. Clear? So here, therefore here how the waves it will be there? It is like this. So this is your direction of your wave. In this wave it is moving now. How the particles are vibrating now? The particles are vibrating like this. Therefore these particles are vibrating like this. So all the particles are vibrating perpendicular to the direction of propagation. All the particles are again vibrating like this no. So how the particles are vibrating? Perpendicular to the direction of the propagation. That means the wave is going, all the particles are vibrating perpendicular to the direction of propagation. So particles are vibrating perpendicular. So these type of waves are said to be like a transverse wave. In this one no, therefore crust and troughs. So here it will be crust, therefore here it will be the trough. So it will create like a crust and troughs. So transverse waves no, therefore best example like a water waves, waves in a string, even we can call it as like a therefore waves in a string, even light is a transverse wave. Light is a transverse wave. So therefore here the compulsory, this is required one medium, this also required one medium. Here particles vibrate parallel to the direction of propagation, here particles vibrate perpendicular to the direction of the propagation. Here compressions and diffractions, here crust and troughs now, right? So in this way, so we can classify or we can differentiate between longitudinal and transverse waves. So the best example, so how you can tell that light is a transverse wave now? Therefore, there is one property is there, so which can classify which is transverse and which is longitudinal waves no? So that is polarization. If any wave are exhibiting the polarization nature, that is said to be like a transverse in nature. So polarization will never exist for our longitudinal waves. Rest of other things no, like interference, diffraction, so superposition, right? So this all both it will be there no, but only the polarization can be separates. So therefore longitudinal and transverse waves. How you can tell light is a transverse waves no? So this is one of the reason, so that light will exhibits like a polarization now. That's why so it is said to be in the light is in a transverse in nature. So these all are the basics related to the waves no, and the classification so related to the waves. Now we'll see some basic terms, right? So terms related to the waves now, basic one terms now, right? So this is a classification, just overall view classification of the waves now. Now we'll go for basic terms. Therefore, to study the waves, no, what are the things you should know it, right? Basic terms in waves, right? Now suppose we'll take it as one wave, no? Suppose here one wave. This is wave it is there. So therefore here when we can say that one complete wave no. So one complete wave. Okay, we'll take one complete wave no. Therefore here, so this is said to be like one complete wave no. Let us take this one no. Here, from here to therefore one crust and one trough. This is said to be like a one wave, right? One complete wave. this is crust and trough. Therefore, here it is having two waves, right? So, this is one complete wave. So, therefore, here the length of this wave, we'll call it as like a wavelength. What is this one now? Wavelength. What is the wavelength now? That is nothing but a length of the wave. Therefore, the total length, the distance of this wave, right? So, the time taken to complete this wave, we'll call it as like a time period. The time taken to complete this one wave, to form one wave, so we can call it as like a time period. Therefore, it is T. So, therefore, number of waves which are generated in 1 second, therefore, that is said to be like a frequency. Frequency is nothing but a number of waves produced or developed in given time. Here for one wave, this one wave, how much time it is taken now? So, one wave, therefore, the time taken is nothing but a T. So, 1 by T is nothing but a frequency, right? So, frequency 1 by second, therefore, hertz onto this. What is the SI unit now? So, you can tell that it is like a hertz. Some basic information now, sometimes. So, we'll study that there will be a wave is there which is having the frequency of 500 hertz. 500 hertz meaning is what? What is the meaning of the 500 hertz? 500 hertz means in 1 second 500 waves. That means 500 waves are generated onto this one, right? So, if they tell that 500 hertz is nothing but a 500, therefore total complete waves produced in 1 second after this, right? Like this you should remember that. So, 500 hertz means, so in 1 second 500, so type these waves are generated, right? So, most important, one very important point now, therefore, that is speed of the wave, very important, speed of wave. What is speed of the wave now? Speed means what is the formula? Speed is nothing but a distance by time. So, therefore, speed is nothing but a, so distance by time taken, by time, you know it. So, for wave, so one wave, therefore, how much distance it is travelled now? Distance travelled is nothing but a wavelength, and the time taken to for this one is nothing but a T. So, wavelength by time period is nothing but our speed, or wavelength into 1 by T, therefore, into frequency, this it will be your speed of the wave. And this formula is applicable for all the waves now, right? So, all the waves you can calculate the speed of the wave, any electromagnetic wave, longitudinal wave, transverse wave, all the waves, no. So, therefore, you can calculate the speed of the wave by using this formula. If the speed of the wave is constant, like the speed of the light is constant, but for different color, therefore, different wavelength will be there, right? So, speed of the light or speed of the wave is constant, so therefore, wavelength is inversely proportional to the frequency. When? So, when speed of the wave is constant. That means, if it is having wavelength is smaller, so therefore, frequency will be larger. That means, smaller waves means it will produce larger number of waves, no? So, if it is wavelength is larger, so less number of waves will be generated. Therefore, wavelength is inversely proportional to the frequency. Clear? So, we will do some questions related to this also. Now, we will go for one more important concept, no? That is speed of the transverse wave, speed of transverse wave in string, in stretched string. There is a one string is there, like you might see guitar is there, guitar string is there, no? If you disturb it, therefore, what will happen now? The wave it will be generated and it will go and it will travel that wave on the string, right? So, we want to calculate the speed of that string, right? Therefore, here this string is clamped between the two ends onto this one. So, this string, no, therefore, here it is connected to some weight of this one, right? Or it is tightened onto this one, understand, no? Now, if you create one disturbance here now, this disturbance, now what will happen now? This disturbance is carried out. So, this disturbance now, therefore, what will happen now? if you create the disturbance now, this disturbance it will create like a one wave here now, right? So the speed of this wave we want to calculate it now, right? So the speed of this transverse wave now we want to calculate. So how to calculate the speed of this wave now? So very simple one now. Therefore we can use dimensional method now to this one now. So the speed of the wave depends on the tension which is created in this one now, tension. So it depends upon the tension which is how much it is getting tightened onto this one now. Tension is nothing but a force. So it depends upon the mass and length of this one no. So we can write down depends on the mass and therefore also depends on the length of this string now. We can use the dimensional method no to derive this equation no. So I will explain this. Therefore next one more is also is there. So at that time you can use the similar concept onto this, right? So here how we can determine the speed of this one now. Speed, so we can use dimensional method formula. Speed depends on, therefore it is proportional to, therefore here proportional to tension to the power of x, m to the power of y, l to the power of z. How we are going to determine it now? Speed. So speed is equals to, so we can write down the dimensional formulas for the speed now. What is the dimensional formula for the speed? So therefore L1, or you can write down, so dimensional formula for the speed no, therefore L1, so t minus 1, that is m0. Clear? So is proportional to tension is nothing but a force is nothing but a m1 L1 t minus 2 whole power x. So m to the power of y into therefore L to the power of z. Clear? So you can simplify it now, just mathematics. So therefore then you can simplify it now. Therefore how? So m to the power of x and here m to the power of y, x plus y, L to the power of therefore x, L plus z, t to the power of minus 2x. Clear? There is no other term like algebra. So here m0, L1, t minus 1. So we can compare the powers onto this one. No? Therefore here x plus y is equals to 0. So x plus z is equals to 1, minus 2x is equals to minus 1. Therefore here x is equals to, so how much it will be? 1 by 2. So here y is equals to minus x no, therefore y is equals to minus 1 by 2. Clear? So here z is equals to 1 minus x no, z is equals to 1 minus x value 1 by 2, therefore also 1 by 2. Clear? So y value I got it, x value I got it, therefore now what I will do, I will substitute all these one now in this formula. So how you will get it now? Here therefore speed, so here speed is proportional to t to the power of x value is how much now? 1 by 2. So m to the power of y value how much now? Minus 1 by 2, L to the power of 1 by 2. Clear? So this we can we can see it now. It is 1 by 2. We can just simplify it no. Therefore here we can simplify it. Right, we will simplify this one no. So here we will simplify. So v t to the power of 1 by 2, so proportional to t to the power of 1 by 2, L to the power of 1 by 2, here m to the power of minus 1 by 2 no, m to the power of 1 by 2. Clear? So here v to the power of all 1 by 2 no, whole to the power of, we can write down t into L by m. So here L I am taking down onto this one no, therefore he is proportional to, so t by therefore m by L. So m by L, therefore m by L is nothing but a linear mass density. That means mass per unit length onto this. Therefore here v, if we remove this proportionality, you can keep the constant no, that constant is given as 1. So therefore it will be equal to t by mu. So this it will be your formula for the speed of the transverse wave in a string onto this, right? So speed it will be equal to square root of t by mu. Clear? So directly proportional to the tension and inversely proportional to the, so linear mass density onto this. Clear? So now linear mass density means what? Lower mass no. So therefore if linear mass density is smaller, So like mass is smaller, length is larger means, so that is thin wire. Therefore, mu is small. Small means what will happen now? That is nothing but a thin wire. Thin wire, right? So thin wire will be having the speed, it will be larger. So in the speed, therefore speed it will be large. That means the wave will travel very faster in the thin wire. So therefore, if mu is larger means, so mass is larger means it should be slightly become like a thick onto this. So in the thick wire, therefore V should be small. That means, so speed of the transverse wave in the thick wire, it will be the smaller. So in the thin wire, it will be larger. And this formula is very, very important, no? So we'll use this formula in most of the applications on this. So remember this. So speed of the transverse wave is directly proportional to the, so square root of tension by linear mass density. Now, clear students, right? So now we'll discuss one more important, no, therefore about the sound waves. Sound waves, clear? So sound waves. So now we'll discuss the speed of the sound wave. Sound is compulsory require the one medium onto this, right? So now we'll discuss the speed of the sound wave, no? Therefore, the speed of sound waves now. Therefore, now the speed of the sound wave. Therefore, the sound wave depends on what parameter, no? Speed of the sound wave, no? Depends upon the, therefore, here it depends on the modulus of elasticity of the medium, right? So, modulus of elasticity of the medium, and it is also depends upon the density, no? Right? So, the speed of the sound in a different medium depends upon the modulus of elasticity and density, no? So, how this speed it will be there now? Therefore, again you can use the dimensional formula method, no? Therefore, here the speed it will be right, directly proportional to the modulus of elasticity and density to the power of y. So, modulus of elasticity, we can write down the dimensional formula. The speed is equals to m0 L1 T minus 1. So, proportional to modulus of elasticity is nothing but a pressure. So, it is like a force by area. Force is nothing but a m1. So, L1, therefore, L minus 1 into T minus 2. So, to the power of x. Density, mass per unit volume, no? M1 L to the power of minus 3 whole to the power of y. Clear? Or we can write down m to the power of x, here power x, power y, x plus y, L to the power of minus x minus 3y, t to the power of minus 2x. So, this is m0 L1 t minus 1. So, therefore, he can compare this one, no? T minus 2x. Therefore, here minus 2x, this power, no? This power. Therefore, minus 1, x is equals to 1 by 2. Here x plus y 0. Therefore, here x plus y is equals to 0, y is equals to minus x, y is equals to minus 1 by 2. I want only these two values, no? Therefore, so these two values, no? What we will do? We will substitute in this equation now. So, v is proportional to e to the power of x. X is nothing but a 1 by 2, density to the power of minus 1 by 2. Therefore, so we can simplify this one, no? So, we can simplify. Therefore, we can simplify this equation, no? Therefore, speed, so is proportional to square root of modulus of elasticity by density onto this. Therefore, we can remove this proportionality, we can get constant, that is constant is 1 E by rho. This is the speed of the sound in a different media. Clear? So, therefore, this is also very important formula. Now, we will write down the speed of the sound in a different media. Therefore, speed of sound, right, in solids. In solids, what will happen now? Speed of the sound in solids, no, mostly you will have the Young's modulus, no? Therefore, it will be Young's modulus by density in the solids. In liquids, right, in fluids, no, in fluids, so like mostly in fluids. Fluids means like a liquids and gases, no? So liquids and gases. So what you can write it now? Speed, it will be equal to square root of. So here Young's modulus will be there for fluids, no? Bulk modulus will be there. Bulk modulus by density. Right? Clear? So whatever the speed of the sound in a gases, how it will be the speed of the sound in the gas. Okay. However, it is in the gases is bulk modulus by density onto this. But what will be the bulk modulus of the gases? No, in the gases there is two bulk modulus will be there. One is isothermal bulk modulus, no, and adiabatic bulk modulus. These two I derived in our thermodynamics part 2. Please go through it. No, therefore how to calculate this bulk modulus of the gases now. So therefore Newton, right? So speed of the sound in gases. So in the gases, no. So Newton, what did he say now? Newton said that, so the speed of the sound, therefore how the sound will propagate now? It will undergo like a compressions and retractions. So in the compressions and retractions, no, he said that, so therefore this will undergo in the form of a isothermal process. So in these compressions and retraction, compression means pressure is changing, pressure and volume is changing, no? So how they are changing? He said that isothermal process. So therefore isothermal bulk modulus is how much, no? Isothermal bulk modulus is nothing but a pressure. So speed of the sound as per our Newtons, it is given as pressure by density. But this is not will not get one correct value onto this. Nearly 300, therefore nearly 290 or like that, you will get the speed of this one. If you substitute here, no, you will get it as nearly 290 meters per second, which is very far away from the measured values onto this. So later on, that is Laplace, what it says now? He says that the sound will propagate not in the form of a isothermal. So therefore Laplace equation. What did he says now? He said that it is not undergo like isothermal process. So these compressions and retractions will undergo in the form of a adiabatic process. Adiabatic process means what? Total heat it will be, net heat exchange it will be the 0. So therefore here, so it will be adiabatic. I already derived this adiabatic bulk modulus of for your adiabatic, no? So adiabatic is nothing but a gamma p. So therefore if you substitute the speed of the sound in gases, no, right? So speed of the sound in gases now it will be equal to, so gamma p by rho. So this it is gives as a correct value nearly 340 so meters per second at our room temperature onto this one, no? So therefore this it will be goes like a correct value. So this formula was accepted for the speed of the sound in gases. Gamma also we discussed in kinetic theory of gases, no, gamma is nothing but a Cp by Cv or 1 plus 2 by F. F is nothing but a degrees of freedom. Please go through it to understand this one, no, kinetic theory of gases now, compulsory, right? So now we got it, no, speed of the sound in gases. So what you got it now? It will be nothing but a gamma p by rho. Clear? So now how the speed of the sound depends upon the pressure and density onto this. So the speed of the sound is independent of the pressure. Why it is independent now? Because if you increase the pressure, automatically density of the gas also will increase. So if you decrease the pressure, the density of the gas also will be changing. Therefore speed of the sound in gases is independent of pressure. Why? If you change the pressure, no, because P by rho it will be equal to constant. P by rho, therefore it will be, so it is constant. Pressure by density, so it will be constant. Clear? So now we will write down some more formulas, no, how it is depends upon the temperature. So speed of the sound, so what you can write it now? Gamma, therefore P, this is nothing but a mass by volume. Clear? So mass by volume, therefore pressure into volume. So PV is equals to nRT. So what I can write it now? Speed of the sound, it will be equal to gamma into nRT by total mass of the gas. So number of moles of the gas you can write down total mass by gram molecular weight, no? So total mass also get cancelled. Gamma into RT by therefore gram molecular weight of the gas. So therefore the speed of the sound, how it is depends now, speed of the sound is directly proportional to the square root of the temperature. That means as temperature increases, what will happen now? The sound speed also will be increases. So higher temperature, the speed of the sound will be larger. At lower temperature, speed of the sound will be smaller. And speed of the sound is inversely proportional to root gram molecular weight. That means if it is heavier gas is there, like you can write it as like a, right, heavier gas is there, heavier gas. For heavier gas, therefore the speed of the sound is less, therefore speed of the sound is less. For lighter gas is there now, for lighter gas, so therefore the speed of the sound, it will be large. Clear? Most of the students, what they will do now, they will confuse in this one now, what will be the speed of the sound in the humid air or dry air, therefore which it will be larger. Humid air or dry air. So speed of the sound in the humid or dry. Most of the students know, they will confuse in this one, no. So humidity means what? Like water vapor is present onto this one. Mostly that is a water vapor. So dry means water, like a nitrogen, oxygen onto this one. So which one will be heavier onto this one? Humid air is nothing but so water, and dry air is nothing but mostly nitrogen or oxygen now. So water is having how much now? It will be oxygen is 16, therefore totally 18 is there, no. So therefore here it will be how much now? 14, 28 onto this. Clear? So which is heavier onto this one now? So dry air, therefore nitrogen, it will be larger. So therefore this is heavier gas, no, this is lighter gas. So speed of the sound, it will be inversely proportional to the gram molecular weight, no. So therefore the speed of the sound will be larger in the humid air. That's why in the night time and in the early morning time, no, the speed of the sound will travel very, very faster, no, compared to in the daytime onto this. Why? Because of due to this reason. No. Clear? So now also how it is depends on this, no, directly proportional to the temperature and inversely proportional to the gram molecular weight. Clear? And it is independent of the pressure onto this. We'll do one question here, no. Right? So we'll do one simple question, no. Speed of the sound at 0 degree centigrade is C, it is 0 degree centigrade is V. So at what temperature in degree centigrade the speed of the sound, it will be 3 times of the V. So 3 is 3 times, right? Now we know it is square root of T. T should be compulsory, absolute, compulsory, right? So here suppose we can write down V2 by V1, right? It will be equal to square root of T2 by T1. So V2 is how much now? This is V2, this is V1, right? So it is 3V by V. This will get cancelled out. So squaring on this, T2 by T1, it will be equal to 3 square. That implies T2 by T1, it will be equal to 9 times. T2 is equals to 9 times of T1. 9 times of T1 you should not use in degree centigrade, always gases, I told, no, always use the kelvins, right? T2 it will be equal to 9 times of 273 kelvins now. But in degree centigrade if you want to calculate, you know, so in degree centigrade, no, so T2, so 9 times of 273 minus 273, so therefore 8 times of 273, no, right? So this many degree centigrade and this many kelvins. Clear? Right? Here 9 times of this one, no, therefore how much it will be? So 9 3 is 27, 63, 65, 6, 18, 20, 2, 4, 5, 7 kelvins. So 8 times, or you can subtract these two. So 2, 1, 8, 4. This is your T2 degree centigrade. It is in kelvins. In this way you can solve the problems, no? And one more some important concept, no? So what will be the speed of the sound? Speed of the sound in helium, right, at 27 degrees centigrade by speed of the sound in nitrogen at 127 degrees centigrade. This ratio we want to calculate it now. So speed of the sound, right, helium and nitrogen. Helium is monoatomic, nitrogen is diatomic. So helium mass is that. Therefore, the speed of the sound we can write it as square root of gamma RT by therefore m. So it is depends upon the gamma, depends upon the T, depends upon the mass now. Therefore, it is proportional to gamma T by therefore it is m. Clear? So therefore we can rewrite it as right. Therefore, directly proportional to the gamma of the helium by gamma of nitrogen into therefore T, temperature of the helium by temperature of your nitrogen into, so inversely proportional. So mass of your nitrogen by mass of the helium. Clear? So here what you will get it now? This is diatomic, therefore this is diatomic, this is monoatomic. So 1 plus 2 by 3, therefore gamma value for monoatomic is nothing but 1 plus 2 by 3, therefore 2 by 3 means 5 by 3, 5 by 3. So 1 plus 2 by 5 diatomic, no? Therefore 7 by 5 into, so temperature of your helium is nothing but 300. So temperature of your nitrogen is nothing but 400 into mass of the nitrogen. Mass of the nitrogen, gram molecular weight of the nitrogen is 28. So helium is nothing but 4. Simplify this one, no? You can get your answer onto this. Therefore here you can write down 2 zeros onto this one, no? Right here 2. Therefore you can rewrite it as, so 5 square is nothing but 25 divided by 3 into 7 into 3 by 4 into 28 by 4. So therefore 2s are, therefore it will be 14s are, therefore 2 1s are, 2 7s are, 7 7 get cancelled, 3 3 get cancelled. So therefore root 25 by 4, that is nothing but 5 by 2. Clear? So so one more important question, no? Therefore what will be the speed of RMS speed of diatomic molecule? So diatomic, right? So by speed of the sound in air, therefore diatomic RMS speed at a given temperature, right? At a given temperature. This ratio we want to calculate, no? What is RMS speed formula? Therefore 3RT by therefore m by therefore gamma RT by therefore m. So therefore same of this one, no? What you can write it now? You can write it as like a 3 by gamma. For diatomic, just now we written, no? What is the diatomic now? Gamma value, therefore 1 plus 2 by 5, that is nothing but 7 by 5. So what you can write it now? 3 by 7 into 5, therefore 15 by 7. This ratio, it will be RMS speed and diatomic, speed of the sound. So at a given temperature, therefore this ratio it will be always equal to constant. It does not depend upon the any temperature, right? So right students, we'll do one more part of this one, no? Like 1 or 2 parts, no? Also we'll do like a numerical part based on this concept onto this, right? So please go through this concept thoroughly. So thank you for watching. Please subscribe to my channel.